Live streaming is on.
Hey everyone, welcome to a geophysical tour of mid-ocean ridges. This is part of the Transform 2022 event. And this is a great event, basically a virtual festival of digital geoscience, all free, all open access for now, and basically as long as YouTube will host us, I suppose. I want to thank our sponsor, curvenote.com. They're really helping out this year, so big thanks to them. And if you want to find the schedule for everything that has and will happen in this event, I'd invite you to go to softwareunderground.org/transform. There's all the links there for all the videos, for the Slack channels where all the discussions will happen asynchronously, so you can come back to this. Remember, you can pause and rewind the video, even if you're watching live with us right now. And obviously, hack the algorithm, so share, like, subscribe, and all of that. So now I'm delighted to hand over to Leo for a geophysical tour of mid-ocean ridges. Over to you.
All right, thanks, Rob. Yeah, it's great to be back at Transform after a few years. And yes, my name is Leo. I'm a lecturer in geophysics at the University of Liverpool in the UK. I work on several different open source projects throughout the Python ecosystem, and also some C projects like the generic mapping tools. And the tutorial that we're gonna go over today is kind of inspired by one of the practical lessons that I do for one of my classes here at Liverpool, where we are taking a bit of a geophysical tour around several processes of the lithosphere. And the one we're going to look at in particular is what's going on at the mid-ocean ridges. Right? So is the buoyancy keeping the ridges up? Are they isostatically compensated? How does the temperature distribution vary with age? And how can we explain that the bathymetry increases with the age of the lithosphere? Right, so we're going to try to do a bit of a mishmash of all of that together with Python coding and a bunch of open source data sets that we're going to use. Okay, so let me get this started and share my screen. And just 1 second. Sorry, just getting the right screen up. Okay, there we go. Okay, so yeah, we're going to be doing a geophysical tour of mid-ocean ridges. You can find all of the content for this tutorial if you go to the compgeolab.org website. So this is the website for my research group. There are also links in the video description on YouTube and on the Software Underground Slack channel. But if you're looking at this in the future and you can't find it, please go to this website. Then click on the little GitHub icon here. That'll take you to our GitHub page. And you can search down here in repositories for Transform. I can't type Transform apparently. So Transform, and that'll show up Transform 2022. So if we click on that, that takes you to the GitHub page. This page has a little bit about what the tutorial is going to be, some information about the event, the live streaming, the intended audience, and some information about how you can take part in this tutorial, whichever way best suits you, either typing along with me as we're going on with this stream, or following asynchronously on your own computer, so reading the code and pausing things as you need in the video, right? There's also some instructions here for how to set up your computer. So hopefully the ones who are trying to do this live have already done so and installed the required things in their computers. If you haven't and you need some help, or if you don't want to bother just because you just want to take a look at the tutorial, there's this handy little button here that says Launch Binder. Right, so by clicking on this, that'll take you to an online Jupyter lab that's running on some free donated cloud provider by the mybinder.org team. and that should have everything already pre-installed. Then you can run the tutorial there. The one caveat with this is it's all running online, so it's not going to be saved on your computer unless you explicitly click on the little cloud button that's on there to save things on your computer for later. Right. So otherwise, if the session shuts off, any code extra that you write might get lost. So just be careful with that. Okay, so what I'm going to do is first I'm going to assume that we have our computers already set up, and then you can download. So if you click on the Mid-Ocean Ridge Geophysics notebook, then there is a little download button here, right? So click on that, and that'll download the notebook to your computer, right? Which is going to look something like this, but that's okay. It's expected. And there's also a version here that doesn't have any of the code, and that's the one I'm going to use to type things out live with you. Right, so I'm going to go ahead and download that. So if you want to follow along, download the empty version of the notebook. And I would actually recommend downloading both, just in case you miss something or you want to double check against my code. You don't have to try to read things in the video. You can copy and paste from the full notebook later. All right, so I have all of these already in my computer, and I'm going to now switch over here to my terminal and start Jupyter Lab. So the one thing I have to do first is conda activate. And I need the name of my conda environment, which is handily here. So I'm going to highlight that and Control-C to copy, or Command-C if you're on a Mac. And I'm going to come over here to my terminal. And usually you can right-click and paste on a terminal, right? So Control-C and Control-V don't really work on a terminal. So I'm going to paste that there. So now I have my tutorial virtual conda environment activated, and once I have that, I can start Jupyter Lab. All right, so then I'm gonna get this long string of things being printed out, and it's also gonna open up Jupyter Lab on my browser here. So it's running on my computer, hence the local host. All right, so once you have Jupyter Lab, you can navigate. So for me, I'm putting that in edu transform 2020. So this is where I have my two notebooks. So just navigate to wherever you put your notebooks, whether that's your downloads folder or somewhere else on your computer. Okay, so I'm gonna go ahead and click on one of these. So I got the empty version, and this is where we're gonna be working from this entire video. All right, so let me maximize this so that we get a lot of screen space. Okay, so as we said before, the title of this tutorial is a geophysical tour of Mid-Ocean ridges. And there are links here to that GitHub repository, the YouTube live stream, and all the licenses, or the open licenses for the text and figures, and also for the Python code listed here. So everything is as Rob said already, free and open access, and you're free to reuse, remix, and share any of this content, including the video itself. All right, so I have some information here about the tutorial. Our main goals is to try to use some geophysical data. In this case, it's going to be gravity, bathymetry, and the age of the lithosphere, to try to answer a few questions, right? So one is, how do these mid-ocean ridges stay so tall, right? How come they don't sink back into the mantle? What keeps them upright? And a related question to that is, are they in isostatic equilibrium, right? So is buoyancy the thing that's keeping them upright, or is it some sort of tectonic force? And then we're also going to try to answer, why do oceanic basins tend to get deeper as they age? Right. So let's see if we can come up with a physical mathematical model that explains this. So along the way, we're also going to learn how to get some equations that describe the physics of these models and transform them into Python code so that we can compare the model predictions against the data that we observe. All right, so you can read things in more detail as we go along. Okay, so first thing we're going to do, as with any notebook tutorial, we are going to import all of the things that we're going to need. Right, so here we're going to use the standard scientific Python library, so NumPy and Matplotlib. for plotting and for numerical calculations. We're also going to use Xarray, which is a relatively new package that is all about dealing with multidimensional data that has coordinates. So think of as NumPy arrays, but where the indices are coordinates, they're physical coordinates and not just 0, 1, 2, 3, 4. So for the type of data we're going to be looking at, and for geophysics in particular, this is really a useful package. It was a real game changer. Then we're going to use a package called Verde, which is one of the projects that I work on. That does several different things with geospatial data. So it handles interpolation, projections, and things like that. We're also going to use Bool, which is another of the packages I work on, that calculates normal gravity so that we can do a little bit of processing on our gravity data. We're also going to use Pooch, which is a tool that we built for downloading data from the internet and storing them on your computer. So all the data that we're going to use, we're going to download them as part of the code. Then we're using PyGMT, which is another project I work on. That's a mapping library that doesn't really depend on Matplotlib under the hood. It uses another tool called the Generic Mapping Tools, or GMT. And you'll see that it's much faster than the other Python alternatives and has a bit nicer defaults, right? So it's easy to plot grids and maps and overlay coastlines and things like that. And then finally, we're also going to use PyProj, which is what handles the actual map projections that we're going to do. Okay, that said, then to the data. So what we'll be using this tutorial is the eTopol1 digital elevation model. This is in the public domain. We're not going to use the full eTopol1 dataset. We're actually going to use a downsampled version of it that's, instead of being 1 arc-minute resolution, it's going to be 10 arc-minute resolution. And this is mostly so that the download that we're going to do here is a bit faster, right? And we don't really need the full resolution for what we're going to do. And otherwise, we'd just be pointlessly waiting here for a 400 megabyte download to happen, right? So we don't need to do that. We're also going to get a grid of gravity that's licensed Creative Commons attribution. This is a global grid of observed gravity, right? So not a gravity anomaly or anything like that. It's just actual observed gravity. So 9.8 something meters per second squared. The units there are actually in milligauss, so 10 to the minus 5, or sorry, 10 to the 5th meters per second squared, at 10 arc-minute resolution as well. And this data was generated from the Eigen 64 spherical harmonic model, right? So it's a model output, but a physical model, not a lithospheric model or anything like that, just a spherical harmonic model of gravity. Then the third data set we're going to use is a model of seafloor lithosphere, or lithosphere age, and this is also licensed Creative Commons attribution. This is a 6 arc-minute grid of global seafloor age that was produced by Seton and collaborators in 2020. So this is the latest version of this data set that's coming out of the EarthBite group in Australia. All right, so now that we know the data sets that we want to download, let's see how we can download them using Pooch, so that we can have the code do the downloading and storing the data, so that we only download it once. Okay, so the way that this is going to work is I'm going to make a variable that I'm going to call, let's say, path eTopol1. So this variable is going to contain the path of the downloaded data set on my computer, right? And this is going to be populated by pooch.retrieve. So this is the main function in Pooch that we use to download data. So I'm going to break the line here to avoid it being too long. And I'm going to type in that one of the arguments I need to give it is the URL of the data. So Pooch can take multiple types of URL. It can be FTP, HTTP, or more recently, it can even download based on the digital object identifier, or DOI, of a data set that's either on Zenodo or Figshare. So this eTopol1 data that we're using is hosted on Zenodo. So this is part of the Fatiando Terra collection of open data sets that we use in all our tutorials and documentation. So since I have here the Zenodo DOI for this tutorial, for this data set, I can copy that, this little number here. So I'm going to go back here to my notebook. So as URL, I'm going to say DOI : and then paste the DOI. The second part of this URL is the file name. So I'm going to put a slash. Then I'm coming back here to Zenodo, and I'm going to copy the name of my topography data set. So that's this. All right. The next thing I need to give it is a known hash. Right. So this is the value of a checksum or a hash that's used by Pooch to verify that the download actually worked and you have the correct data file, right? Not some random data file that maybe the server changed or something like that, or maybe the download was corrupted. Luckily, Zenodo also puts in the MD5 hash of this data set, so I can copy that and just paste it here, right? So when the download happens, Pooch is going to verify that the checksum for the file it downloaded actually matches what Zenodo says is the actual hash of the file. Another nice thing we can do is say progress bar equal true. Oh, I forgot to run. So sorry, I forgot to run the import cell here. So let's run that. And now that it's executed, things should actually work. Okay, so that's it. So when I hit Shift Enter here, then oh yeah, sorry, I forgot to reset things on my computer. Let me do that. Oh, apologies, I muted myself for some reason. Okay, so let's try that once again. So now that I've reset things on my computer, when you first run this cell, Pooch is gonna check your computer for the file. If it doesn't find it, it'll download the file and place it in the directory that's shown here. Right, so it's saying here in home Leo .cache.pooch. That's where the data set was downloaded to. Okay, so the data set gets downloaded here, and this path etuple1 is going to be this value here, right? So /home/Leo, or whatever it is on your own computer. The neat thing about Pooch is if I run this cell again, no download happens because Pooch finds that, oh yeah, this file already exists on your computer and it matches the known hash. So I don't really have to download it again, and it'll give you the path without doing the download. So you can run this as many times as you want, and you only download one version of the data. So that saves you a lot of bandwidth. Okay, so I'm going to be lazy here and copy and paste this. And then I'm going to change this to path gravity. Right, and let's remove all of this as well, and the MD5 here. Okay, so now let's download the gravity data set. So I'm going to open this link. Right, so I got gravity, and this is part of the same collection of open data that we've generated. So once again, I can copy the Zenodo DOI. Right, so I got the DOI. I can copy the name of the grid. I'm going to copy that here. And finally, I can copy the MD5 into the known hash. And then when I run this, I should see a little download happening, right? So now we're downloading the gravity data to my computer. And as a final step, let's download. So path seafloor age. And let's download now the seafloor age. So let me clear this and the hash. So let's click on the seafloor age to go to the EarthBite group website, and there's the data set right up here, and they handily put a link to the data here. All right, so this takes us to this HTTP mirror of an FTP server. The data that we want are in grids, and we want this grid here, right? So age GTS 2012.6M. So this is the 6 arc minute version. They also have a 1 and a 2 arc minute versions, but we don't, these are substantially larger downloads and we don't really need that much resolution. So let's just get the 6-minute version. So what I'm going to do is right click on this and copy the link, right? And then that link I can paste here as the URL for Pooch. Right, so this is the thing that it's going to download. Unfortunately, we don't know the hash of this particular grid because the EarthPike group doesn't publish the hashes of these so that we can verify them. So if you don't know the hash, Pooch lets you say that the known hash is none. So notice that no quotation marks. So this is the Python value none. And so when I run that, it's still going to do the download. All right, so it downloads the file. And then handily, it does say that, well, I downloaded this file, and this is the hash of that file. Right, so if I copy this and put it into known hash, then the next time I run, Pooch is going to verify that the data set is actually the same one that I downloaded this time. Right, so it's not the ideal case scenario, but it's better than having no checks at all. Right, so once again, if I run this one more time, nothing changes there. Right, so the download doesn't happen because the data set is already on my computer. Okay, so now that I have all the paths and I have the data downloaded, what we can do is load these grids, which are in netcdf format. Right, we can load them with Xarray. So let's load here, for example, first etuple1, and this is going to be equal to xr dot load data array. Right, and the Xarray function needs the path to the data file, and we have that right handy here in our path etuple1 variable. Right, so if I do that and I put etuple1 by itself at the end of the line, at the end of my cell, when I run this code, the data gets loaded into the etuple1 variable, and Xarray has a very nice here HTML representation of the grid for Jupyter notebooks. Right, so these are the grid values. We know that there's 1,081 points in latitude and 2,161 points in longitude. It tells us that this is a float 32 array. It also gives us the longitude and latitude coordinates, and all of these have a lot of metadata associated with them, right? So the units, the range, the name of them, and the data set itself has a bunch of metadata. So this is where it comes from, the citation, and all of that. Right? There's a bunch of extra information in here, including units and the long version of this. So, right, so this is height and topography, references to mean sea level. Okay, so we can do the same with gravity. So gravity is xr dot load data array and path gravity. And then let's put gravity by itself to verify that it works. So we got gravity here. And finally, we can get seafloor age equals xr dot load data array and path seafloor age. Then I put seafloor age by itself here. All right, and we have a question on the Slack here about whether it's possible to use Pooch to download from Google Drive. So right now, I don't know, actually. I haven't tried. I imagine that if you have a plain HTTP link to the data set on Google Drive, that you could. But if it's redirecting things here and there, or if you need to access it through an API, then we might have to type things out to maybe implement some custom downloader in Pooch. But if that's something that you would like to have, and you have kind of an idea, please open an issue on the Pooch GitHub repository. So if you Google Python Pooch, that should give you Pooch here. So any of these links is gonna have the bug tracker link here, or just the source code link, and open an issue requesting the feature, and we'll see if we can work on that. right? Okay, so let's keep going here. Okay, so now that we have our grids, one thing that you might notice is the seafloor age grid. One, the name of the coordinates is different. Instead of latitude, longitude, it's just lat long. And the number of data points is different because these grids are in different resolutions. So later on, when we want to, for example, plot bathymetry versus seafloor age, or do any kind of modeling relationship between bathymetry and seafloor age, we are going to have to co-register these grids, which means have them both be at exactly the same points in space, right? So we'll talk about how to do that in a little while. Okay, so but that's a problem for us in the future. So for now, let's try to plot these grids and see what these data sets look like. All right, so for this, I'm going to use the PyGMT library, which, I mean, you could also do exactly the same thing with CartoPy and Matplotlib, but I find that PyGMT is usually faster and has more support for map projections and coastlines and things like that. That's kind of out of the box, right? So with CartoPy, that requires some customization. And for certain projections, it can be very slow. All right, so let's see how we plot these grids with PyGMT. So first, I'm going to make a figure variable that I'm going to call fig, and this is going to be pygmt.figure. Right, then I'm going to call fig.grdimage. So this stands for plot a pseudo-color image of my grid, and I need to give it the grid I want to plot. So let's say e-tuple1. I can specify the color map, so cmap equals, and GMT has a color map called e-tuple1 that's made specifically for e-tuple1 topography, so that's very handy. I'm also going to specify that the projection is a Mulvity projection, so W, because I think it looks nice and rounded. And as part of the projection, you have to say the physical size of the plot. So I'm going to say 25 centimeters, just so that we get a decent size of plot. Another option that GMT does out of the box is if you want to do hill shading on your grid, you can pass in an option called shading. And if you just want the default shading, you say shading equal true. And that's all you need to do hill shading, basically, in PyGMT. Okay, so now I have that. So I can add a fig.basemap so that I can plot a frame around my map. So here I'm going to say frame equals true to get the default frame. Then I can do a fig.colorbar to put a color bar so I know what the values represent, or what the colors represent. And finally, I can do fig.show to display my map on the Jupyter Notebook. All right, so let's close that and run this. So that takes a little while because it's trying to plot this grid that's not very small. So now we get like a nice, beautiful map here with very few lines of code. Notice that the topography is hill shaded and all of that, and it's nicely placed. You got the tick labels and everything that you would kind of do manually on CartoPy. As an added thing, if I want this to be the preview figure to be larger, I can give the width argument to show, and let's say, for example, 800 pixels. So when I run this again, now my figure is going to be a bit larger in my notebook and easier to see, right? So I find that, yeah, it's for maps like these, it's better to get them as large as possible on your screen, right? So this looks pretty good. You can tell that it's kind of low resolution topography, but it's still good enough for what we're going to do. Okay, so let's look at gravity next. So I'm going to copy that code and paste here. And I'm going to change this for gravity. And the color map I'm going to use is the Viridis color map from Matplotlib. So we got access to all of these custom Matplotlib color maps in PyGMT. And I'm going to remove the hill shading here because I know that it's going to look kind of bad. All right, so let's run this. So same map projection and just a different color map. And this is global gravity. So notice that the units here are 975,000 or to 908,000 milligauss, which is about 9.75 and 9.8 meters per second squared. With this, it's nice if I can overlay some coastlines, and I can do that by saying fig.coast. And then I can ask it to plot shorelines with the default values, right? So I'm going to say shorelines equals true. And let's run that. All right, so this gives us nice shorelines plotted on top. Now, I find the black here kind of difficult to see, particularly around the equator. So let's try to make this white. To do that, instead of passing true to shorelines, I can pass in the string white. Right, so that sets the color. And you can also tweak the thickness, the resolution, and there's all sorts of things that you can do. Remove these little tiny little wiggles and all of that. GMT has options for all of those. All right, so now we can see that gravity pretty much just varies with latitude, right? That's the main thing that happens, is that gravity is stronger at the poles and weaker at the equator. If you ever took a geophysics class, this is probably one of the things you've learned within the very first few lessons. And this happens because of two effects. So one, the Earth is flattened. So on the poles are slightly closer to the center of mass of the Earth than the equator. And also the Earth is spinning. So when we talk about gravity, what we actually mean is the sum of the gravitational acceleration due to the attraction of the masses, and also the centrifugal acceleration because of the fact that the Earth is spinning. And when we're on the surface of the Earth, we feel this as a acceleration that's pushing us out of the Earth. So if you add those two effects, what you get is gravity varying, increasing towards the poles. A secondary effect that we can see very faint here is around the Himalayas, around the Andes, and some of the major subduction zones. There's a very faint signal here that disturbs this overall gravity field, right? So these large tectonic events, in particular the subduction zones, they have a very large fingerprint on the gravity that we measure on the Earth. All right, so finally, let's copy and paste this again, and let's plot the seafloor age. And for this, I'm going to use the Inferno color map just because that sounds really cool. And once again, I'm removing the shading, and let's run this. All right, so now I got seafloor age as a map. And for this as well, let me add the fig.coast shorelines equal true so that we get the outlines of the continents a bit better there. There we go. Okay. So we can see that this grid only has values in the oceanic basins, right? So there's nothing on the equator, on the continents, and usually close to shore, we also have no information about the age. A particular pattern that you can spot is along the middle of the Atlantic and a bunch of the other oceans. We have these stripes of very young oceanic floor, and it gets progressively older as we move away from these things, which are the mid-ocean ridges. And most of the oceans are in between 0 to maybe 150 million years old, which in geologic terms really means that they're babies. Right, and we only have a few patches of very old lithosphere, for example, here around the coasts in the Atlantic, in the Pacific, and in particular around the Mediterranean area. Right, but almost everything else is very young. Okay, so there's a little tip here that there are several different color maps that are supported in GMT and PyGMT, and they're called CPTs in the GMT documentation for color palette tables. And there's a handy little link here that'll take you to a page that lists all of them with plots. So you can pick and choose the one you like best. Okay, so now that we have all our data, we've plotted it into maps. So let's first have a look at a bit of a global state of the oceans and mid-ocean ridges. And let's see if we can figure out what's their isostatic state, right? So are the ridges in isostatic equilibrium, which means that they are the height of the ridges is supported by their buoyancy on top of the mantle, or are they supported by other forces, right? So tectonic forces or something else. One way for us to try to answer this question is by taking a look at gravity. If we look at something called a gravity disturbance, right, we know for a fact that gravity disturbances should be small or close to zero in regions that are in isostatic equilibrium following an Airy-Heiskanen or Pratt-Hayford model. So these are local compensation models, not something like the flexural model. Right, so what we can do, since we have our gravity data, is calculate gravity disturbances, plot them on a map, and just check if they are small or close to zero at the mid-ocean ridges. Right, so we can do a simple visual inspection for this. So nothing too fancy, but something that we can easily do with the data and open source tools that we have. Right, so the gravity disturbance is defined as the difference between the observed gravity, which is what we have as a function of longitude, latitude, and height above the ellipsoid, and something called gamma here, which is the normal gravity. Right, this is the amplitude of the gravity caused by an ellipsoid that's spinning. So something like the WGS84 ellipsoid that's used for a lot of positioning and things like that. So we have the observed gravity already. All that we need is to be able to calculate normal gravity at the same points as we have observed gravity. Right? And the Boole package is something that was created specifically for this. Right? Boole defines a lot of these ellipsoids, and it provides methods for calculating the normal gravity due to these ellipsoids. So let's see how we would calculate a gravity disturbance using Boole. Right. So what I'm going to do is make a variable that I'm going to call normal gravity. Right. And this is going to be the gravity of the WGS84 ellipsoid calculated on the same points where we have observed gravity. Right. So let's say we're going to use Boole.WGS84. WGS84. And the WGS84 has a method called normal gravity. And what we need to give it is the latitude of the points. So let's say it's gravity.latitude. Right? So gravity is our gravity grid, and dot latitude are the latitude coordinates of this grid. And we also need to give it the height. Right? So I got that in gravity.height. Right, which is the height of observations. In this case, it's a uniformly 10-kilometer height. So once we do that, we have normal gravity calculated on all the points that we have gravity observations. So we can calculate the gravity disturbance as our observed gravity minus normal gravity. And this is going to give us a gravity disturbance as a grid. Right, so that's basically all we need to calculate the gravity disturbance. One thing you may note is that we didn't need to give the longitude here, and that's because these ellipsoids are symmetric along the longitudinal direction, so their gravity is also symmetric and doesn't depend on longitude, so we don't need to specify it here. All right, so now that we have that, let's make a plot. So let's be lazy and copy here. Let's copy this one, because I don't want to type that out again. So let's copy that and plot the gravity disturbance instead. And I'm going to use the polar color map, and I'm going to say +H here. And I'll explain what that means in a little while. And so for the shorelines, let's make them a different color, right? So for example, GMT and PyGMT, they accept HTML hexadecimal codes for colors. So if I say 999999. This is going to be a kind of middle light gray color. And you can freely ignore this warning here. It doesn't really mean anything here. Right, so this is the gravity disturbance. This plus H sign here, what it does is it tells GMT that it should apply something called a hinge to the color map, and that fixes 0 as the white color. Right, so no matter the distribution of colors that we have, 0 is always going to be white, and then it's going to progress towards blue to one side and red to the other side. So this is really a handy thing to have for 2 characters, in PyGMT. Okay, so what do we see here, right? So if we look at where we knew there were mid-ocean ridges here in the middle of the Atlantic and the Indian Ocean. So if we look at the ocean itself, it's mostly very small, close to 0 gravity disturbance, particularly here in the Pacific and here in the Atlantic. Right? So this is an indication that the mid-ocean ridges, they are indeed supported entirely by their buoyancy. So they don't have tectonic forces acting on them. Where we do have tectonic forces acting on topography, for example, in subduction zones, like here in the Caribbean, in the Andes, in the Himalayas, and here around Japan and the Pacific, these are places that have very high gravity disturbance because the topography is due to tectonic forces. It's not really due to buoyancy. Another place where you'll see large gravity disturbances is oceanic islands. Right, so we have Hawaii here, and we have here the Canary Islands, and so on. And these all have very high gravity disturbance values. And the reason for this is these oceanic islands aren't supported by their buoyancy as well. They're supported mainly by the rigidity of the oceanic lithosphere. So that's what keeps these islands up. It's not the fact that they are less dense than the mantle underneath. Right, so that's a handy little visual inspection. And so from here on out, we can kind of assume that, yes, indeed, the mid-ocean ridges are supported entirely by their buoyancy. So now, enough with the global stuff. Let's try to zoom in on one particular ridge system so that we can take a closer look at what's going on there. Right, and for this this example, I've chosen a region in the South Pacific, and this is a section around the island of Rapa Nui, or Easter Island. Let's take a look at that more closely. And for this is where X-array really shines, is we can index those arrays using the actual coordinate values. We don't have to figure out if longitude X is equivalent to pixel Y in the image, right? We can just give it the coordinates and it'll know what to do. So, okay, so the way I'm going to do this is to specify a region, right? And this region is going to be the west, east, south, and north boundaries of my region of interest. Right, so I have here, let's say longitude minus 170 until longitude minus 80. And I'm going to do latitude minus 65 until latitude minus 10. Right, so I picked these out by looking at this area on Google Maps and trying to figure out the coordinates of the corners. So you can do this however you want, really. All right, so let's put a little comment here that this is west, east, south, north. Right, so once I have my region, what I can do is slice the grids. So let's get the disturbance for the Pacific. So disturbance underscore Pacific is equal to my gravity disturbance grid. And to do this in X-array, we're going to use .cell. Right, so the .cell method is what allows you to select parts of the grid by their physical coordinates. So here I'm going to say that the longitude is going to be a slice, open parentheses, and it's going to be a slice from the value in region 0 until the value in region 1. Oh, sorry, 1. And the latitude is going to be a slice of the value in region 2 and the value in region 3. Right, so this is going to give me a smaller grid that fits between these boundaries. So let's do the same thing for eTopo 1. So eTopo 1 Pacific is going to be eTopo 1 dot cell. And here's a handy little trick that you can do in Python. So I'm going to say longitude again equals slice. And if I want to give slice the first 2 arguments of region, I can do something called list unpacking in Python. So if I do star region from 0 until 2, right, the star here tells Python to pass in the elements of this region one at a time to the function. Right, so this is a handy little shortcut that you can use. And let's say latitude equals slice, and then star region 2 until the end. Right, so that makes the line a little bit shorter, so it's nice and compact, and you don't have to type out region all over. And finally, we can get the seafloor age for the Pacific, which is going to be equal to seafloor age dot cell. And remember that for the seafloor age grid, the coordinates were lat long and they weren't latitude and longitude. So here, let's do lon equals slice star region, and the 0 is implicit, so I can do just colon 2, close parentheses, and lat equals slice star region, square brackets, 2 colon, square brackets, and parentheses, and one more. Right, so when I run this line, now I have 3 versions of the grid that are sliced to the South Pacific. So let's make a map of these and see what they look like. So once again, I'm going to be lazy and copy my PyGMT code down here. But instead of gravity disturbance, I'm going to plot the disturbance Pacific with the same color map. But since this is now a small region, instead of the Movidi projection, which is the W here, I'm going to use a Mercator projection, which is an M, uppercase M in PyGMT. And the rest I'm going to leave the same. All right, so let's run that. So this is my little region in the South Pacific. And we got some oceanic islands here and there. And we've got the mid-ocean ridge system running through here. All right, so as we can tell from the gravity disturbance, this is mostly in isostatic equilibrium, except for these little island chains and a few fracture zones here and there. Right, but overall, we can consider that the ridge system is in isostatic equilibrium. So let's once again be lazy and copy and paste. And now, instead of the gravity disturbance, let's plot the eTopo 1 bathymetry for the Pacific. And here I'm going to use the eTopo 1 color map. And let's plot that. All right, so now we got eTopo 1 with varying here from minus 6,000 meters in the deepest parts all the way up to 0 or so in some of these little islands, right? So one curious thing is we can see the main mid-ocean ridge system here. That's shallow bathymetry going steadily to deeper bathymetry, and it's offset by these transform faults, right? So this is very classic from anyone who did any sort of plate tectonics in school or university. You've probably heard about all of these things, right? The mid-ocean ridge system spreading out and being offset by transform faults. One curious thing in this particular region is this thing here, right? So let's look at the seafloor age data, and that's going to show up a little bit nicer. So let me copy this and paste it there, and let's do seafloor age Pacific with the Inferno color map. All right, so now when we look at seafloor age, we got the main ridge system here at a very young age, all offset by the transforms. A very curious thing we can see in this region are these little bits here where we have very old lithosphere suddenly being cut off by a younger lithosphere, right? So these really look like old subduction zones that were aborted at some point. And another curious thing is you got that region of shallow bathymetry, that little line of shallow bathymetry coming up, that is very young lithosphere as well. So this is a second mid-ocean ridge system that's intersecting the first one. So this little thing here is a triple junction, right? Which is a neat little puzzle for the people researching plate tectonics. Okay, so yeah, so we got all these data sets, and now we need to prepare them so that we can try to come up with a relationship between bathymetry and the age of the seafloor, right? So see if we can kind of build a quantitative model for this. And for this is where we go back to, now we kind of have to deal with the fact that the seafloor age and the bathymetry grid, they aren't calculated on they aren't produced on the exact same points. So until we co-register them, right, which means calculate them both on the same points, we can't really do this type of analysis. So now we really have to deal with this fact, and we have to prepare the data so that we can actually analyze what we want. All right, so to get both grids calculated on the exact same points, we're going to do 3 different steps. Right, so one is we're going to project the 2 grids using a Mercator map projection so that we can deal with Cartesian coordinates instead of geodetic coordinates. This is going to make it a lot easier for us to do things like interpolation and downsampling of the grid. The second step is to downsample the age grid to about 10 arc-minute resolution. Right, so we're going to go from a 6 arc-minute grid into a lower resolution 10 arc-minute grid, so that it kind of roughly matches the bathymetry grid. And finally, once we've done that, we can then interpolate the age values on the same points as we have bathymetry, so that our 2 grids are going to be at exactly the same points. Right, and most of these things we're going to do with the Verde library, right, which is kind of made for this particular task. So let's do step 1 then, project the grids. Right, so to do this with Verde, I can use Verde, which I imported as VD. So let's see, vd.project grid, right? So very explicit function name there. This takes a grid. So let's say we want to project a topo 1 for the Pacific only, right? And it's going to take, let's look at the documentation here. So it takes a grid, a projection, and a method, right? So the method here is what it uses to sample the points from the grid. So we're going to set that, and we need a projection function. So this is where, before we can do this, this is where we need PyProj, which provides these map projection functions. So let's make a projection here. So projection is going to be equal to PyProj dot proj with uppercase, right? So the casing here is important. So this is going to create a projection function for us. We're going to put another argument here called proj equals and the string merc, which means make this a Mercator projection function, right? And I always find it kind of funny that I'm writing pyproj.proj. That's quite a mouthful to say on a live stream, and quite repetitive actually to type out, but yeah, it's a fun little thing. Another thing I can give as an argument to the projection is the latitude 0, or the latitude of the center of the projection. And I'm going to make this the mean latitude of my data set, right? So let's say etopo 1 Pacific dot latitude dot mean. Open and close, and then close here. Right, so this is going to give me a projection function that I can then give to Verde so that it knows how to do its projection. So here I can give it the projection, and as a final argument, I'm going to say method equals the string nearest. so that it does a nearest neighbor lookup instead of trying to do linear interpolation, which is going to be slower. Right, so I'm going to save the result of this in a variable that I'm going to call etopo1 Pacific underscore proj. Right, so this is going to project the topo1 grid, and let's do the same thing for seafloor age. Right, so seafloor age Pacific proj is going to be equal to verde.project grid, open parentheses, seafloor age Pacific projection, and the method is equal to the string nearest, and close. All right, so let's run all of this and see what we get. So we are still getting these two little warnings, but don't worry about these. This is like an internal thing for Verde, and it's already going to be resolved by the next release, but it's not causing any errors in your data. This has actually not yet been fixed. This link here is to an open issue. So if anyone's looking for some low-hanging fruit to contribute to an open source project, this might be a good place to go. All right, so with that plug aside, so now that we have our grids in Cartesian coordinates, right? So these are easting and northing coordinates instead of being latitude, longitude. So now we can downsample the grid, the age grid, to about 10 arc-minute resolution. All right, so the way we're going to do this is by taking the mean value of age in blocks that are about 10 arc-minute in size. And the reason why we do this block reduction instead of simply taking every other point is to avoid effects like aliasing. Right. So another way to do this would be to first do a bandpass filter, or sorry, a low pass filter on the grid, and then we take every other point. Right. But alternatively, taking these blocked means is a lot easier to do. Okay, so to do this, we're going to create an age table. So we're going to convert the grid that we have into a table of numbers, right? So easting, northing, and age as 1D arrays, just because Verde expects that as input. So we can use verde.grid to table to make this conversion, and I'm going to give it the seafloor Pacific proj. Right, so this is going to make pandas data frame as a table. And another thing I might want to do is drop the not a number values from this grid, right, which mark the regions where we don't have age data. So I'm going to do that. And so now I have my age grid. Then I can create a block mean operator that's going to be equal to verde.block reduce. Right, so block reduce does these operations by calculating whatever you want really inside of these spatial blocks. The first argument you need to give it is what you want it to calculate. So for me, I'm going to give it np.mean. Right, so the mean function from NumPy, that's what I want it to run on every single block. And the second argument I'm giving is the spacing, which is the size of the blocks. So as we said, we want roughly 10 arc minutes. So we're going to kind of do a little estimate here that 10 over 60 would be 10 arc minutes in degrees. And we know that 1 degree is about 111 kilometers around the equator. So this is like a rough estimate, right? So 10 over 60 times 111 to the 10 to the 3 meters. All right, so now we have our block reduce. And then we can do, finally, we can actually do this block mean calculation. So we're going to get coordinates for the age, for the block mean age, and we're going to get the mean age. This comma mean age is going to be equal to block mean dot filter, right, which is how you execute the block mean in Verde. And this is going to take a couple of arguments, right? So one of them is the coordinates. So this is the coordinates of the input data. which in our case is going to be the age table dot easting and the age table dot northing. So these easting and northing are standard names that Verde applies to things when instead of calling things X and Y, because in general they will be easting and northing. So this is a bit more intuitive and easier to read. Finally, I need to give it the actual data that it's going to calculate the mean of, which in this case is age table dot z, which is the variable name that's on the EarthByte grids, right? So that's what that is. So when we run this, then Verde does this blocked mean operation. So now we have a downsampled version of the age grid. And we have another question here on Slack. So is there any utility to export process grids to netcdf or GeoJSON TopoJSON? So yes, there are. Xarray can load things in GeoJSON format. It does that through the raster.io package, if I'm not mistaken. And so once you have things as an Xarray dataset or data array, you can save them out to whatever format you want. So that can be netcdf, it could be GeoJSON, it could be maybe not GeoJSON, but GeoTIFF at least for sure. And new formats like ZAR or whatever else grid format is available, really. So Xarray has a lot of exporting functionalities. In terms of TopoJSON, I'm not entirely sure. I haven't used that before, but I bet there is some sort of tool or plugin for Xarray that handles that. If it is at all possible, then I'm sure that it's already implemented somewhere. And if it's not, then asking for this sort of functionality is something that helps the developers guide their process. So if that's something you need and it doesn't exist yet, I would highly recommend getting in touch with the developers and asking nicely if that's something that they would want to implement, or maybe it's something that you want to implement yourself and contribute that. All right. So hopefully this answers the question. Okay, so continuing on here. So finally, now we can interpolate this age data onto the same points as the bathymetry. So we have our downsampled age, and so now what's left is the interpolation. So we're also going to do this with Verde. So I'm going to say interpolator is going to be equal to verde.scipy gridder. Right, so this is a Verde interpolator that calls the Scipy interpolation functions in the background. I'm going to say method equals nearest as well to use a nearest neighbor interpolation, just because that's quite a bit faster for running live now on the tutorial, but you may want to use some fancier interpolation for your calculations. All right, so interpolator. Then once I have my interpolator, I can say interpolator dot fit and give it some the input data. So in my case, it's going to be the coordinates age and the mean age. And once I have a fit interpolator, kind of like a scikit-learn regressor class, once you have that, you can use it to make predictions. So Verde has a neat little method called interpolator.grid. Right, so grid is going to do the prediction on a regular grid, and it's going to spit out a Xarray data set, right, which is very convenient. Okay, so for the grid method, I'm going to give it a few arguments. So one is going to be the coordinates where I want it to generate the grid, because I don't just want any grid. I need a grid that's in exactly the same coordinates as the etopo1. So as coordinates, I'm going to give it etopo1 Pacific proj dot easting and etopo1 Pacific proj dot northing. So this way I can guarantee that my two grids are going to be exactly co-registered. Another argument I can give it is the data name. Right, so this is for the metadata used within Xarray. So what is the data variable going to be called? And in this case, I want it to be called seafloor age. All right, so notice that this has to be a list. with one string. And this is because you could have multiple things that you're interpolating. So for example, if you have data that are for velocity vectors, there's two components there. So when we grid with Verde, we are usually interpolating two different variables. So that's something that can happen. All right, so now that I have this, I'm going to put the result of this in a variable that I'm going to call grid. So grid equals interpolator.grid. And let's put grid by itself here to see what it actually is. Okay, so running this with the nearest method, this is quite fast. And what I get is an X-array data set that has the eastern and northern coordinates, the same ones as I have for topography, and it has a variable called seafloor age. That's a grid of seafloor ages that were first downsampled and then interpolated. So now that we have this grid data set, we can add the eTopol1 to this same data set. So we can merge them together and have everything in a single variable. So let's say grid equals xr.merge, and I need to give it a list with the grid that I had before that just has the seafloor age plus the eTopol1. So if I put grid here again, eTopol1, let me run this again because I messed up there. So create the grid again, and of course this is not the full eTopol1, it's the eTopol1 Pacific Proj. All right, so when I run this, if the grids are co-located or co-registered, then there should be only one set of coordinates because X-array recognizes that they are the same for both grids. So now we have a single variable that has both my seafloor age and my topography grid. So I can operate on them both together. Okay, so finally, let's make some maps. So I'm going to come back here and copy these and scroll back down. So paste here, and now let's plot grid.seafloor age. So this is going to be the downsampled version of my seafloor age. Oh, yeah. So since I have projected coordinates now, I can't really tell PyGMT to try to project this again as a Mercator projection. So I need to say plot these as just Cartesian coordinates. And the code for that is to pass the projection called x. All right, so with that, and since I have that, I can't really plot coastlines anymore. So remove the coastlines, and that's what I get for copy and pasting instead of writing things out, right? You make mistakes. All right, so now I have my downsampled seafloor age that's projected in Cartesian Mercator coordinates. And let's copy this one and plot grid.topography with eTopol1. And let's see what that looks like. All right, so now I have my bathymetry. It's considerably smoother the age is considerably smoother than what we had before. And I also have the bathymetry here, and they're both co-located. All right, so now that we have that, we can actually make a cross plot, right? So let's plot bathymetry on the y-axis and age on the x-axis, and let's see if there's any relationship between them. So for this, I'm going to use Matplotlib. So plt.figure, plt.plot. Right, and for plot, I'm going to say grid.seafloor age. And since this is a grid and I just want to plot some points, I have to first get the values of the grid, and then I can ravel the array. So ravel transforms a grid into a one-dimensional string of numbers, right? Which is what I need for matplotlib.plot. So let's do the same thing. So grid.topography.values.ravel. And I can instruct matplotlib to also plot with dots instead of lines. So I pass it the string. That's just a full stop. Right, so that's all I need. Okay, so I got a figure here. Let's make it a little bit larger. So I'm going to do fig size equals, let's say 14 by 9, and pass this to plt.figure. And that gives us a much larger plot. let's also add a call to plt.grid so that I get some nice grid lines. Okay, so I got here the bathymetry on my y-axis and the age on the x-axis. So clearly here there's some sort of relationship, right? They decay with age. There's some large-scale relationship between these two variables, but there's also quite a bit of noise, right? It's very, very noisy, particularly around the deeper bathymetry. We got points that are very shallow for their age and points that are kind of deep for their age. So this can create a little bit of a pattern and kind of hide the overarching pattern that we're looking for, because these little things here, these are all the oceanic islands and all those things that kind of don't fit well with a lot of the large scale models that we have. Right, so let's see if we can get rid of all of these little oceanic islands and tiny features. We're going to do that by downsampling both grids together. Right, so by downsampling them again, we are going to smooth out all of these small scale features. So to really guarantee that we get rid of most of these islands, we can downscale down to about 1 degree resolution, which is roughly 100 kilometers. So that should get rid of most of these tiny islands. Now that we have everything in a single X-array data set that has Cartesian coordinates, a very handy method for downsampling that does almost the same blocked operation that we did with Verde is the Corson method in X-array. So we can make a grid underscore course by calling grid.Corson, right? And what we have to tell Corson is in the easting direction, take every 6 points, right? So every 6 points, it's going to calculate a mean or a median or whatever you want. And since our original resolution was 10 arc minutes, then every 6 points is going to be roughly 1 degree resolution. So easting 6, northing equals 6. And we also have to tell it what to do with the borders where it can't get 6 numbers, depending on whether or not the number of grid points is or is not a multiple of 6. Right? So here we can say that the boundary is going to be handled by, let's say, trim. Right? So trim means if you can't get 6 points, just throw out the remainder. Right, and that should be fine for us. So we're going to trim the boundary, and the final thing that we can do is dot mean. Right, so we're telling it to every 6 points in easting and northing, take the mean of those points as a new value. Right, we could also use the median, the standard deviation, whatever else we want to calculate. But for this case, mean is good. So let's put grid course by itself. Right, so now we have a grid with many fewer points. Right, before we had I don't know, like 200 something, and now there's only 55 and 90 points by latitude and longitude. And with this one little concise line, we apply this to however many data variables we have. So again, this is the beauty of things like X-array and why it was a real game changer for people doing science with gridded data sets like this, right? So it's super handy. I highly recommend picking it up if you haven't already. All right, so now let's plot our course grid and let's see what that looks like. All right, so let's copy the bathymetry here in particular. All right, so copy this and let's do grid course dot topography, and let's see what that looks like. All right, so we got a course in topography. We can still see the mid-ocean ridge system, so the triple junction over here. We still see a few of the transforms, but all of the tiny little oceanic islands, those have all been smoothed out. Right, so ideally they shouldn't be a problem anymore for our data set. So let's check that by repeating our cross plot. So again, copying the code for that and pasting here. And now I can say grid course, seafloor age, and grid course topography. All right, so plotting this here. So now we have our smooth relationship which could be maybe a little bit too smooth, but still we can see the overall pattern is that you get this this nice little decay of bathymetry with age until you reach a certain point where it kind of levels off, right? So the question we have now is, can we predict this relationship with a physical model? Right. So hopefully we will be able to. And now that we have our prepared data set, we can try to do that. Before I go there, there's a question on the Slack. So is it possible to overlay with temperature, salinity, and magnetic data? Oh, sorry. Please skip this question if it's out of scope. So no, it's not out of scope. I imagine you mean in PyGMT. So you can overlay things. It's just that if you're plotting a grid with full, without any opacity, then you're going to plot things one over the other, and you're only going to see the last thing you do. But in PyGMT, you can control the opacity of the image. So you could, for example, plot a bathymetry with some sort of opacity, a bathymetry, sorry, and then overlay something that's slightly transparent on top of it. Right? You could do that. Another method for blending things like this is to get use one variable as the hill shading factor for another variable. Right, so this is very often done with the topography providing the shades for another data set like gravity or magnetic. That can distort the data a bit, so I would be very careful when doing that. A more sensible way to do all of this is to plot one thing as an image and then plot something else on top of it as contours. That way you don't really overlay things, and you can see both data sets and try to look at different patterns within them. Right, so that's probably the least likely way for you to kind of mess up your data visualization. So I would recommend doing that. And yeah, you can absolutely do that. All right. So moving on here. Okay, so our next step then is to try to model this with a physical model. Right, for this, I'm going to call on something called the plate cooling model. Right, so this has been around for a few decades. You can find all of the details for this in the great geodynamics book by Turcotte and Schubert. This is a classic geophysical textbook. I highly recommend it. It's very good, and with the data and the code that we're writing here, you can actually reproduce a lot of the plots in that book. Right, so a lot of this class that I'm teaching came from kind of my nerdy desire to reproduce the content of that book as open source. And I'm very happy to say that, yeah, a lot of it, it just pans out. It really does work. So that's a real testament to the book. So I highly recommend that. Right, so the plate cooling model, it describes the temperature distribution and evolution of the oceanic lithosphere, right? All the way from its formation at a mid-ocean ridge to its evolution as it cools and moves away from the ridge with time. Right, so this sketch here is a little bit of the model layout. Right, so we got a symmetric system here around the ridge. So we only really need to consider one of these sides because the other one's going to be exactly the same. So here we have the lithosphere forming at the ridge, right? So at the ridge, at time equals 0, we have only a stenosphere. We don't have a lithosphere. As time moves on, the lithosphere that formed starts cooling and thickening. Right, and this cooling is going to spread downward into the lithosphere, right? And the boundary between the lithosphere and the asthenosphere is going to be defined by an isotherm, right? Which would be this surface down here. So the way that the model is set up is that we assume that the spreading rate is constant, right? So that's going to be this u velocity here for how fast the new lithosphere moves away from the ridge. And if we assume that, we can kind of substitute the distance from the ridge with the time or the age of a particular block of lithosphere. Right. Second is we assume that the heat conduction only happens vertically, right? So heat will escape from the lithosphere into the water, but it doesn't travel horizontally, right? With that simplification, we can describe this entire thing by a 1D diffusion equation, right? So this little equation here, which is a classic little diffusion equation in one variable. In this case, the depth z and the time t. And alpha here is the thermal diffusivity of the lithosphere. So if we apply boundary conditions on this, such that the temperature at the top of the lithosphere is held constant at t equals 0, so this would be the temperature at the ocean floor, and that we also hold the temperature at a particular depth, ZL. If we hold that constant to an asthenosphere temperature, which would control the maximum thickness of the lithosphere, right? And we also put an initial condition where the temperature profile with depth starts off as all asthenosphere temperature. We can arrive at a solution to this diffusion equation that looks like this thing here. Right, so this again can be found, and all the equations below can be found in the Turcotte and Schubert book. So this gives us a temperature distribution with depth and time. All right, so while this is a very useful physical model, we can't really measure temperature with depth to any reasonable depth, right? That's a very difficult thing for us to measure. So testing the model with regards to temperature is going to be very difficult. Luckily, we can try to predict bathymetry based on this temperature distribution. Right? To do that, we can assume that the oceanic lithosphere is in isostatic equilibrium, which we know to be true given the gravity disturbances that we just saw. So if we impose the condition of isostatic equilibrium, and we assume that as the lithosphere cools down, that its density increases with a linear thermal expansion coefficient, alpha v. Then if we try to balance out the masses and the pressure at a given compensation depth for isostasy, we can actually arrive at an expression that gives us bathymetric depth as a function of lithospheric age for the plate cooling model, right? So that is this rather large equation here that has a bunch of different terms, right? So WR is the depth of the ridge. The rows here, so rho m and rho w, are the density of the mantle and density of water. Alpha v is the thermal expansion coefficient. Ta and T0 are the temperatures at the asthenosphere and the surface. ZL is this maximum thickness of the lithosphere. Then we have an infinite sum here with m equals 0 until infinity, and an exponential here that depends on the thermal diffusivity alpha, the age of the lithosphere t, and some constants. Right, so the depth here doesn't enter into anywhere because that's integrated over when we derive this equation. So this has a bunch of physical parameters and two observables that we have, right? We have the age and we have the W. So if we have that, we can kind of code this model up and see if we can predict the W versus or bathymetry versus age data that we actually have. Okay, so let's make a function that calculates this model. All right, so let's try to do that. Sorry, just 1 second. Okay, so let's try to calculate this function. Right, so to make any sort of Python function, we can use the def keyword. right, to define a function. And I'm going to call my function, let's see, what did I call it in the notebook? Plate model bathymetry. All right, then we open parentheses to start listing all the input arguments that this function is going to take. And since I know it's going to take several, I'm already breaking the line preemptively here. So when I hit enter, now I can start listing all of the arguments that this is going to need, right? So one, this is going to be a function of age, so it absolutely needs to take the age of the lithosphere, right? It's also going to need WR, which is the ridge depth. So I'm going to call it ridge depth instead of calling it WR because, you know, what is WR? I have no idea. Ridge depth, I know exactly what that is. So I highly recommend always using very descriptive variable names. Okay, so ridge depth, I'm also going to need the temperatures, right? So temperature at the surface, which is T0, and the temperature of the asthenosphere, which is TA. Right, I'm going to need ZL, which is the maximum thickness of the lithosphere. Then I'm going to need the thermal coefficients, right? So the thermal expansion coefficient, alpha V, and the thermal diffusivity, which is alpha. I'm also going to need then the densities, right? So the density of water, rho W, and the density of the mantle, rho M, right? And that's basically all I need. So once I have my function, let's put a little doc string here. So I'm going to put triple double quotes. And inside, I'm going to kind of write a little bit about what this function does, right? So this calculates the predicted bathymetry from the plate cooling model, right? And if I want to be extra diligent, I would list parameters. And here I would list everything. So age is going to be what, and so on and so forth, right? But in the interest of time, I'm not going to do that here. But you absolutely should, because you'll thank yourself when you're using your own functions. Okay, so I've got all of these. The first thing I'm going to need to do is make sure that the units are all compatible. So I had written a little argument here about the temperatures being all in Kelvin. The distances, so the ridge depth and all of that, are going to be in meters. Ages are going to be in million years, because that's what we have in our data. Thermal diffusivity is usually in millimeters squared per second. And the thermal expansion is in 1 over Kelvin. And the densities are kilograms per meter cube. So the thing that I'm going to really need to make sure aligns is the thermal diffusivity needs to go from millimeters to meters, and the age needs to go from million years to seconds. All right, so that's something that I'm going to have to convert. The rest all kind of line up already. Right, so let's first do the thermal diffusivity. All right, so thermal diffusivity in the right units, to go from millimeter squared to meter squared, I need to multiply by 10 to the minus 6. So 1e minus 6 times the value that I had in millimeter squared. So that should give me meter squared per second. And finally, the age needs to be converted from million years to seconds. So I kind of like doing this in steps because I find that easier to remember. So first, let's go from million years to years. So that's going to be 1e6 to do that conversion. So 10 to the 6. Then I can go from years to days. So that's 365.25, right? So 365 days and a quarter, roughly, times days to hours, so times 24. Then hours to minutes, 60, and minutes to seconds, another 60. All right, so all of that times the age in million years should give me the age in seconds. Okay, so I have the age, and now I kind of need to transform this huge thing here into code. one very neat thing about Jupyter Lab that I like to do when I'm doing this sort of coding is I'll right-click on the top tab here, and I'm going to say New View for Notebook. So this opens up the same notebook, but in a side panel. All right, so then I can adjust here the thickness, and I can scroll down. And with this, I can have the equation on one side here and my code on the other side. So I don't have to scroll up and down. I can just look at the equation on the side. This is also very handy if you're comparing plots or if you need to be looking at a plot in order to write something or to code something. So opening these multiple views for the same notebook is a really handy thing. And this is only possible in Jupyter Lab, not in the classic Jupyter Notebook. Okay, so now we need to calculate this whole thing. The tricky bit here is probably going to be calculating this summation. So let's do that one first. So whenever you see a summation like this in maths, in terms of code, you need to think for loop, right? So the natural mapping of a summation into code is a for loop. So to do that, we need to start with, so let's say summation equals 0. So we start with a neutral value. So if we're summing, the neutral value is 0. If we were multiplying, the neutral value would be 1. Right, so here we start with that. And then we're going to do for, and the loop variable is going to be the same as the summation variable to make it easier to map. Right, so for m in range, so from 0. And unfortunately, I can't do something like numpy.infinity for my summation because my code would run forever. But luckily, this decays with m, right? So it decays with m in the exponential and outside of it. So that means that I can truncate at some point where the coefficients of the summation start becoming negligible. So I could be thorough and try to calculate for a given precision how far do I need to go in my sum. But if we're being lazy, let's just say 100, and we'll see where it goes from that. Okay, so now that we've got that, the way we evaluate the summation is by saying whatever I had in summation, or the new value of the sum is going to be equal to whatever I had before plus the whatever I'm adding to that. So what goes inside of these parentheses is whatever is inside of the summation. Right? So first thing I have is 1 over 1 plus 2 times m squared. All right, and that's going to multiply a exponential. So we're going to do np.exp, and open a parentheses. And since I can tell this is going to start getting large, I'm going to break the line and close the parentheses. All right, this is another recommendation I would have is always, when you're breaking a line, break it on the opening of the parentheses, and then immediately close it right underneath. So this way, if I see an opening parenthesis here, if I want to check whether I closed it or not, I just go to the beginning of the line and look straight down. So if I see a parenthesis there, I know I've closed it. If I don't see one, right? So let's see, there's this one. I go to the beginning of the line, I go straight down. There's no parenthesis there. I know I'm missing one, right? So this is a neat little trick also when you're coding a bunch of mathematical equations. All right, so now let's put what's inside the exponential. So this is going to be minus t, which for us is age, times alpha, the thermal diffusivity, right, times numpy.pi squared, right? And let's break a line there, and times 1 plus 2 times m squared. So this is all that goes on the top of the exponential, right? And then let's break a line again, and then we divide this by the max thickness, ZL squared. All right, so that should be it for the summation. If I did everything correctly, we'll verify that shortly. Now I can calculate the bathymetry, or the depth here in this case, or no, sorry, not depth, the bathymetry that I'm going to predict is going to be, and again, this is going to be long, so I'm going to preemptively open a parentheses and immediately close it so that it, again, if I open it, it has to line up perfectly here. Okay, so now I can actually calculate that. So the first term here is WR, which is the ridge depth. Right, so it's going to be WR plus, and this is going to get a bit long. So again, I can tell it's going to be long from the equation. So I'm going to open and close a set of parentheses, and I'll type whatever's in there to the right. So what's inside there is rho m, which is the density of the mantle, times the thermal expansion coefficient, alpha v. Then, again, I'll break the line. So times temperature asthenosphere minus temperature surface, right? And let's break the line again. So times the max thickness, right? And then I'm going to divide by open parentheses, density of the mantle minus density of the water, and close parentheses. All right, so since I have this practice of opening the parentheses and immediately closing it right underneath, once I'm done, I don't really have to go back and check that I closed every single parentheses, because I always open and close them at the same time, right? Okay, so that closes this one, right? So that's this term here, and now that whole term needs to be multiplied by another large thing here, right? So that's going to be 1/2, or 0.5, times 4 divided by numpy.py squared, right? And all of this is multiplied by the summation, which I already calculated, and that's in my summation variable. So that's not that long, so I can close the parentheses here. And once I have that, I can return the bathymetry, right? And that should be it. Hopefully I did everything correctly. So when we run this now, I have a function now that's called plate model bathymetry that hopefully predicts the bathymetry accurately, right? So since I'm done with this, I'm going to close the new view. And okay, so now that we have our function, we can try to predict bathymetry and see if it actually matches the observed bathymetry, right? So we're going to assume these input parameters, right? So the ridge depth, if I go back to my cross plot here, I can tell that the ridge is at about 2,500 meters, right? So let's assume that. So 2,500 meters for the depth of the ridge. Then I'm going to assume a density of water as 1,000 kilograms per meter cube, so nothing controversial there. Density of the mantle as about 3,300 kilograms per meter cube. Temperature at the surface to be 0 Celsius or 273 Kelvin. The temperature of the asthenosphere as 1,600 Kelvin. The thermal diffusivity as 1 millimeter squared per second, and a thermal expansion from that's 3 10 to the minus 5, 1/Kelvin. So these values I got from the geodynamics book, right? So copy this straight out of there. So let's see if we can fit our data with these values, right? Okay, so let's do, what did I call this? Bathymetry underscore plate. So bathymetry of the plate model is going to be plate model bathymetry, open parentheses, and again, open and close and break a line because I know that this is going to get long, right? So let's say the age data is going to come from our grid, right? So it's our grid course dot seafloor age. Right, then our ridge depth is going to be 2,500. Our temperature at the temperature at the surface is 273. Our temperature at the asthenosphere is 1,600. Our maximum thickness, So this I didn't include in the table here. I just realized that. But let's assume that it's about, I don't know, 100 kilometers, right? So 100 E3. Then we can do thermal diffusivity equals 1, d thermal expansion Did I not include this as an argument? I did. Oh, okay, so thermal expansion is going to be 3 e to the minus 5, so 3 times 10 to the minus 5. And finally, the densities. So the density of the water is going to be 1,000, and the density of the mantle is going to be 3,300. Okay, so with that, I'm going to put bathymetry plate here by itself just to see what we got. So let's run this. All right, and here is where also we run into the beauty and magic of Python dynamic typing and Xarray. So notice that in the function here, this has no information about what each of these variables are. Right, so I'm not really saying that this should be a grid, this should be a value, it should be an array, this should be a table. It doesn't really matter. The operations are all that matter. So if I give it a grid, an Xarray grid, I get a grid back. If I gave it a single value, right? So if I gave it like 100 million years, then I get back a single value. If I gave it a NumPy array, I would get back a NumPy array, right? So to me, that's the main beauty of all these tools. So I can give it a grid and I get a grid back. So this is my predicted seafloor age. So let's try to plot that, right? So let's scroll back up here and let's get this plot. And let's see how our prediction matches the observed bathymetry, right? So instead of grid coarse topography, I'm going to put bathymetry plate here. Right, so immediately I can tell that something's wrong, so I'm getting all positive values. And that is because I'm calculating a bathymetry here, but I'm giving it a positive ridge depth. So what the model actually calculates is the depth. It's not really the bathymetry. So to get bathymetry from depth, I need to multiply it by -1. Right? So -1 times, or let's do it down here to make it clearer. So if I return -1 times bathymetry, then that's actually what the values that I should get. So let's run all of this again. And now I get something that looks a bit closer to what we had before, right? So we got a prediction here that has a mid-ocean ridge with shallow bathymetry, and then it gets deeper as we go further away. All right. So yeah, this looks. Oh no, this is the other way around. Bathymetry plate. So I clearly calculated something wrong here. Reach depth. Okay, so I'm going to cheat and I'm going to open up my pre-calculated notebook and let's see what I typed out incorrectly. Oh yeah, I think I already know without even looking. So, because I made this mistake before. So one mistake I made here is this half minus 4 pi. I actually typed in half times 4 pi. So this should be a minus there. And let's run this again. And okay, so now I got something more sensible. Now I have shallow bathymetry in the mid-ocean ridges and deeper bathymetry as we move away. So let's do our cross plot again. So let's scroll up here. Let's copy this and scroll back down. And here. So let me plot this value, and then I can add plt.plot grid course seafloor age values ravel, and I can plot bathymetry plate dot values dot ravel, and I can plot these as red dots, so dot R. And let's check. And as you could probably tell from the little comment that was below here, the model really fits the data really well, actually. So the plate model is known to fit the depth progression of bathymetry with age very, very well. Right, so you can tell that it has the same level of decay, and it also stabilizes at some point. Right, previous models that we had for this, which was the half-space cooling model, it kept on cooling forever, and so it didn't have the boundary condition of a fixed temperature at the base of the lithosphere, which meant that the bathymetry just kept increasing and increasing forever. Right, so the plate model was designed to fix that problem, and you can see that it does so pretty well. Okay, so to recap a bit of what we did, and to do that, I'm going to demo something else here from Jupyter Lab that I really like, is if you click here, you can get this nice little table of contents for your notebook, and these are all clickable. Right, so if I want to go back to a particular section, I can click here and it takes me back there. Another handy thing is if you click on this, you get numbered sections automatically as well. So yeah, it took me quite a while to figure this out and notice that this was added, really. But yeah, it's really cool. Okay, so as we're nearing the end here, so to do a little recap, we downloaded a bunch of grids of topography, gravity, and seafloor age using Pooch that downloaded and stored the data on our computer. We loaded the data with Xarray and plotted the data with PyGMT to get some beautiful maps. We assessed the overall isostatic state of the mid-ocean ridges by looking at gravity disturbances that we calculated using the software Boole. And we realized that, yes, all the mid-ocean ridges are in isostatic equilibrium. We then used Xarray to slice a region in the South Pacific that has a nice little triple junction. And we prepared our data by making sure that both bathymetry and age were calculated at exactly the same points, so the two grids line up. Once we had that, we tried to implement the plate cooling model to see if it could predict bathymetry given lithospheric age, right? So does the model actually fit the data? And we saw that once we predicted bathymetry, that our model fits the data very well, right? And again, this is kind of expected because I did not choose these input parameters at random. They were chosen because, one, I got them from the book, and the authors of the book chose them because they knew that they would fit the data. Right, so if you change any of these parameters, in particularly the maximum thickness of the lithosphere and things like thermal diffusivity, thermal expansion, the density of the mantle, all of these are going to have an impact on the model predictions and how well it fits the data. All right. So to finish off, I kind of want to leave you all with some ideas for things that you can try now that you kind of know how to do these. You have the data at your hands, you have a notebook, you have the software, you have it all at your fingertips and at your disposition. So there's much more that you can do with all of this than what we had time to cover here. Right. So the first thing I would recommend is to make a function that calculates the temperature distribution for the plate model. So basically get this equation and implement it in code, and then do a little plot of temperature as a function of depth and lithospheric age, just so that you can get a sense for what a thermal cross-section of the lithosphere would look like. Second, you can compare. And you can compare all of this with the plots in the geodynamics book. The second thing that I would recommend you trying is zoom in on a different mid-ocean ridge system around the world. So pick another one, somewhere in the Atlantic, in the Indian Ocean. There's plenty of subduction zones out there, and verify for yourself whether or not the plate model works for them, or is this something that's really only valid in the South Pacific, right? And a question that you may have is, will you have to change the input parameters in order to fit the data? And if you do so, what does that mean about the properties of that mid-ocean ridge system, right? About the lithosphere that's being generated there and how the spreading happens, if you have to change some of these parameters in order to fit the data. Then as a final thing that maybe you could try is try to calculate the maximum depth, the thermal expansion, and all these different physical parameters. You can try to calculate them through an inversion, right? So this would be a nonlinear inversion because of the underlying equations, but you could use something like the Scipy optimize library to minimize the sum of squared differences between the data and the predictions to see if you can maybe find optimal values for these parameters given the input data, right? So I guarantee that this is not going to be super easy to do, particularly because inverse problems tend to be difficult. But it's definitely a worthwhile thing for you to practice and learn, because this is lessons for this, for anything regarding machine learning and things like that. It's all the same underlying mathematics. So it's a very worthwhile goal to pursue. And finally, I'd love to see what you come up with. So if you use the cells below here and add more as needed, but code away and see what you can come up with. And please, if you do, share what you discover, the plots you make, and your notebooks and stuff. You can share them, and we can get feedback and discuss. So you can do that by either opening an issue on the GitHub repository, and there's a link here, or post it on the Software Underground Slack group, either in the T22 Wednesday More Geophysics channel, or in basically any other channel, and just ping me. So I'm at Leo Uieda, basically everywhere. And yeah, I'd love to see what you come up with, and happy coding. Thanks for sticking around through all of this.